Hello, class. This is the number 6 recording. So we're going to discuss the third method for computing complex power. So in this case, we will study when the voltage and the real and reactive power are given, how are we going to compute for the current and the voltage drop? So the circuit diagram of this one is like this. This is transformer, and then the transformer has a primary side and secondary side, and then you can collect two loads. You can have a different load connect to it. Imagine this is your house. You can turn on your stove, and you can turn on your heater. Each time you're turning on, you turned on an appliance, you put them on, then your power will increase. So in this case, we have a 24-hour profile. So this is from hour 1, 2, 3, 4, 5, 6, and then this is 7, 8, 9, 10, 11, 12. So altogether, there are 24-hour profile. The reason I times this by 1,000 is because this is in kilowatt. So if I times by 1,000, that would be turning this into watt. I have also given you a PV profile. So in case 1, we won't consider PV. So we can just put this as 0. So in this case, the PV will be none. And then in the second case, if I set case number equals to 2, then it will follow such a PV load profile. So the PV actually have a rated power at 4,500 watts. And you can see this is normalized. So at night is 0, and then this is 7 o'clock, starting from the sun comes out, and then the PV output will slowly increase, okay? And then currently I only set up case equals to 1 and 2, and then so if you don't have these two numbers, then it will send an error message, okay? So the power factor is calculated this way. We usually only have the real power because for the appliances, normally the rated power is the real power it consumed. So depending on this power is resistive or inductive, for example, if this is a heater or incandescent light, then the power factor equals to 1. If this is a motor load, then it could have a inductive load, and then the power factor will be smaller than 1. Usually this is inductive. So I just randomly put some numbers here, 0.9, 0.85, 0.9. So to let you see what the power factor setting will affect our total power consumption. You can see that the total power equals to the real power divided by the power factor, and then minus the power of PV. Because the PV is a generator, so it's a negative load. That's why we put negative sign here. So in case 1, because the PV equals to 0, so you literally just don't have any PV at this household. So the Q will equals to, once we computed the complex power, we can times the square root using 1 minus power factor. So that would be the sine theta, which is the reactive power consumed. And then we can plot them out. So let's just clear everything. Just start from here. Run selection. And then we can clear everything and then just run this part. You can see that this blue one is the reactive power, and the red one is real power. So at night, because power factor equals to 1, so you can see that the real power equals to the complex power because there's no reactive power. And then start from hour 7, you will have some reactive power. The reactive power is increasing. And then this hour 12 to hour 18, the reactive power is higher because I have this basically 0.85, and also the power is increasing. You can see that this is reactive power increasing. So if I set this power factor to be 1.0, let's see what will happen. Let's run that again. You can see that if I set the reactive power, the power factor to be 1.0, then there will be no reactive power. You can see the blue line becomes 0, okay? And then there's only the complex power equals the real. So you can see the black line and then the red line will overlap with each other. So let's just put this back, comment out this one. And then, so if I make them lower, say 0.6, let's see what will happen. This is 0.6. So you can see if I put 0.6 here, then the reactive power could be really, really high. And then you can see this red one is the real power. And then this reactive power could be even higher than real power for some period of time, okay? So let's just set this back. Normally in our household, the reactive power is not that high. So usually using 0.9, it will be okay. Let's see, 0.95. So you can see that this is a regular profile. Usually we can see this is the reactive power. The red one is the real power. Okay. So here is suppose we set this to be case 2, then that means that this household has PV in there. So I'll take this profile, and then you will see that now the total power will change. You can see that because the PV is negative load, this is your PV output. When you plus this one and the real power, the actual power, then the net load is the black one. So you can see that if we plot one more here, you can plot P, and then the actual is, so this is a load, S load. So we plot out the S load here. Let's see what the S load look like. Okay, so S load. Let's just use a K, but a dotted sign. Let's put this line width to be, say, 2. Okay, so let's run that again. You can see that this dotted black line is actually the complex power of the load. And then this dotted line actually is the one that if we don't have a PV on site, then what the complex power would be. But with the PV on site, the real power produced would be the red minus the green. So now our complex power, you can see, dropped significantly, even below 0. So this means here, this is 0. So during this period of time, I'm not consuming any power from the grid. Instead, I actually send power back to the grid. So this is because during this time, I'm actually generating this much power. However, the actual power consumed is only this much. So the power is generated minus the power consumed. I still have some extra power sent back to the grid. Okay. Here are the drawings. Okay. So this is how you would compute for the complex power, because the power is given. So the complex power computing is really easy. The next thing that we can do is to compute the current. You can see that there are 24 values. So I need a for loop to compute for that. So at hour 1 or hour I, it equals the conjugate of a P load plus 1J times QI. So this Q is a Q reactive power consumed by the load. The reason I need to times 1J is because this is complex power, okay? So assuming all the PV generated power is real power, so this would be negative because the PV is generating instead of consuming. So you use the P load minus PPV plus 1J times Q. So this would be the total power consumed. Remember, the complex power actually equals to the conjugate of current times of V. So you actually S equals to V times conjugate of I. Okay. So if I compute for I, it actually should equals to conjugate S divided by V. Because here V is actually, I should put the conjugate here as well. V. The reason I don't have to do that is because in this particular case, my V, V is a reference, so V, the angle is 0. So I do not have a complex part for the V. But ideally, I should put conjugate sign out here as well. Okay. So now I can compute the current. You can see this is the magnitude of the current, and then this red one is the real part of the current. Okay. So next, we're going to compute for the voltage drop here. So as we can see that we can think about this as this is my transformer. Okay. And this is the P plus JQ minus PV. Okay, so this is a load, this is load. So suppose I have a line leading to this this consumed load. There would be a impedance, which is the Z line. So this impedance will have a delta voltage drop. So if I want to compute for the V load here, then what should I do? Basically, what I can do is I can use the V minus the I, because I already computed I in our last section. And then the I times this Z line would be the delta V. Okay, so that's how I compute the V load. So I want to plot out the V load to let you see that suppose this secondary side, I maintain the voltage at 120. When the load is increasing, like you have a power increasing here, then the current will increase. When the current increase, then from this transformer secondary side to the load, there's a line carry out the current from the main grid to the load. So what would be the voltage seen at the bus, the load bus? So you can see that our required voltage is plus minus 5% of the nominal value. So nominal value is 120. So your upper limit is 120 times 1.05, and then your lower limit is 120 times 0.95. So this is the upper limit, this is the lower limit. So what I want to see is to see when the load current increase, whether or not at the load bus, the voltage will drop below the low limit, okay? So what I can do is I can use, this is a matrix, and then I have also a matrix of current and times the Z line. So this would be the load voltage. I can simply compute the voltage that way. I also computed V load voltage with power factor equals to 1. So why I do that? So when I do that, I only computed for the real part of the current. I assume that the load is power factor equals to 1. So if this power factor is equals to 1.0, then what will happen? You can see that if the power factor equals to 1.0, then I only consume the real part of the current, then the voltage drop is actually lower. So that's why we want to do reactive power compensation, because we want to provide this reactive power locally. So you can see that if I have the power factor not equal to 1, the voltage would drop below the load limit. But if I provided the reactive power locally and then make the power factor equals to 1, I only need the main grid to provide the real current. So in that case, my voltage drop can be limited. So one of the effective way to provide voltage support is to add a capacitor here, so that the reactive power needed for this particular load is provided by the capacitor bank. Okay. So I will upload the code to the GitHub. You can play with it. The other thing you can actually do is to actually come here, and then you can actually also put in a PEV here. So suppose you have an electric vehicle, you can also put in some value here as if you're charging the load. For example, if you want to charge at night, only from midnight to 6 o'clock, then if the EV is like a 6 kW, then what you can do is that you can have PEV equals to 6. Suppose you charge 3 hours, then it is full, then you can put 0, 0, 0 here. And then you can see that if you have an EV at your home, and then you only charge them at 1 to 3 a.m., then what the voltage drop would be, and then how the load profile would change. So by using this code, you can actually simulate a residential household. And then you can see that when you have different kind of load connected to the house, how the voltage will change. How this you can see that how the voltage will change. Suppose your transformer voltage can be maintained at 120, then what would be the load side voltage look like? Okay.